Hi, I'm Utsha Bhattacharya. I have done a project on face recognition using eigen faces as a part of the course EEL 6825 pattern recognition. So, why is face recognition needed? Primarily for security purposes. So, these days, with the rise in needs of security, face recognition has become a very important part of it. What we usually do is that we distribute ID cards, RFID cards to authenticate a person, but it's not enough. Like, what if it lands in the hands of a wrong individual? So, in that case, face recognition is very useful. And moreover, for biometric authorization for government ID cards, there also face recognition plays a major role. These days, online banking, criminal investigation, in each of the fields, face recognition does have very important role to play. So, directly jumping on the methodologies, how we do face recognition. One of the very key concepts of face recognition is principal component analysis. What is it? It's a very important statistical tool that extracts out the most prominent features from a distribution of face images. It's very popular. It's a very popular tool. So it's mainly motivated from the concepts of information theory. As we know from the key principles of information theory, pertinent, relevant information will be extracted out from each of the face images in a distribution and efficiently encoded. After that, this encoded face image will be compared with all the face images in the distribution set, which are also encoded similarly. This is what PCA does actually. So, and one of the major advantages of using PCA is that it can deal very efficiently with data of high dimension. How it does that, we'll see later. So, and one of the other major concepts of our project is eigenfaces. So whenever we use the term eigenvector in the field of computer vision, it's called eigenfaces. We do not really use the term eigenvector, but we use the term eigenfaces. So as we know from PCA, we extract out the most relevant information from a face image, the principal components of the distribution of faces. What is that? This is nothing but the eigenvectors of the covariance matrix of the set of the face images. It's exactly that. So these eigenvectors are the features that characterizes the differences between the different face images, the variations between the face images. These eigenvectors are called eigenfaces. As we can see from the image, it looks rather ghostly. So how is face recognition done using the eigenfaces approach? It mainly consists of two steps. First is training the recognizer, and second is face detection and recognition. So how do we train the recognizer? We first gather a training set of M images. Each of them has a dimension of n by n. So it's the training sample. We then transform each image into a face vector. The face vector has a dimension of n squared into 1. So after that, once we have converted each image into a face vector, we normalize them. How do we do that? We find out the mean face vector and then subtract each face vector from that mean face vector. Why do we exactly do that? By doing this, we eliminate the common features from each of the images, so that each image is left with only their characteristic features. So once we have done that, we calculate the eigenvectors. For that, we need the covariance matrix, right? So we know that covariance matrix equals to A transpose, where A is the matrix constituting the normalized face vectors. So as we can see from the slide, C has a dimension of n squared by n squared. That is huge. So it's not really feasible to find out eigenvectors from such a huge amount of data. So what we do is that we use the matrix L, A transpose A instead. What does it do? Why do we use that? It reduces the dimension. So it reduces the dimension. So, and with thorough mathematical mathematical procedure, we have found that the eigenvectors of C and L are almost the same, and they are related as ui equals to avi, as we can see from the slide. So that helps us to map all the m eigenvectors of L to those in C. So we use the dimension of m into m to find out the eigenvectors in a dimension of n squared into n squared. So dimension reduction really helped us. And now that we have found the m significant eigenvectors in L, that is and then in C, what do we do then? We do not keep all the m eigenvectors, we keep only the significant k eigenvectors. Why do we do that? As from the principles of PCA, the first eigenvector has the most prominent features stored in it. The succeeding ones have lesser amount of prominent features in them. As we can see from the picture, the first few have the most relevant information, and the succeeding ones have rather noise in them. So we use only the prominent k eigenvectors. So once we have found the k eigenfaces, what we do is that we represent each face image in the training set as a weighted sum of the eigenfaces and plus the mean image. So the first eigenface, as from the picture we can see, the first eigenface contributes W1% to the top image. The second eigenface contributes W2% to the top image. By doing that, we create a matrix of weight matrix. Like all the weights are stored in a matrix for each face image. So we create a weight vector for each face image, as we can see from the picture. So now that we have trained our recognizer, it's time for us to recognize an unknown face. So whenever we input an unknown face image, we convert that face image into a face vector, as we have done earlier. So once we have done that, we normalize that, which means subtracting the mean face vector from the input face vector. Once we have done that, we represent that input face image as a weighted sum of the k eigenfaces. That gives us a matrix of weight vector matrix of that input face image. Once we have calculated that, we will calculate the distance between the weight vector of the input face image and that of all the face images in the distribution set. If the distance is less than the threshold, then good news, it's a match. If it's not, then it's an unknown person. So what we have gathered what I have gathered from this project is that I know now for sure that eigenfaces is really simple to use and very easy to code, and it can rather handle large data sets. Once I have calculated the eigenfaces of the entire data set, face recognition can be done almost immediately, like in real time. And one of the important advantages of using eigenfaces is that it does not deal with features, our usual notion of features like nose, eyes, etc. It takes into consideration a global feature of each human face. So that is really useful. So in this project, I have used AT&T dataset. It consists of 400 images of 40 individuals with 10 face images per person. Each image are of the same size. Like that is a prerequisite for using PCA. And each individual has images with varying lighting conditions. Each of them are adequately lighted, but they are in varying lighting conditions. So all of the individuals in the images have different poses, like some are smiling, some are winking, some are sad, some are happy, some without glasses, some with glasses. So now it's time for demo. So this is my face recognition folder. as I go to the folder of images, there is a gallery which consists of the training sample of images. As we can see, all the images are of same size, all the images have varying light conditions, and all have a straight frontal position. And this is the probes folder, which contains images which we want to test against. Like these, I can use each of these images one by one for testing, whether it's a known individual or not. So I've already run the program. Now I'll just choose one image from my probe folder. Let's try with amber. I'll keep the threshold as 1. These are the two inputs that it asks for when I start the program. So as I can see, these two are different images, and the program has successfully recognized this person as Amber. And it's a positive result. Let's try a negative result. Let's try with Jill instead. As we know that it asks for these two inputs, let's change the eigenvalues to 10. Let's see what happens. Okay, so no match. So it successfully recognizes each person as I try each of them from the probes folder. Now let's look at the eigenfaces that were created while running this program. Okay, as we can see, it looks rather ghostly. So this brings us to an end of this video. So I'll just end this video.